Humanity has always looked up at the night sky, wondering what's out there. In 2025, we finally have answers from the latest space missions and discoveries from 2024 through early 2025, and they're more unsettling than we ever imagined. The James Webb Space Telescope and other advanced instruments have found cosmic objects so strange that they challenge our understanding of reality itself. Today, we're taking an updated journey through the universe's most incredible phenomena, from cosmic voids spanning 330 million light-years where photons struggle to cross the emptiness, to stellar corpses that refuse to die. These aren't fairy tales. They're real places you could theoretically visit. Our first stop takes us to a discovery that emerged from studying the very fabric of space itself, the supervoid that defies physics. The Boötes Void represents one of the most unsettling discoveries in modern astronomy. This cosmic desert spans approximately 330 million light-years across and sits roughly 700 million light-years away from Earth. To put this scale into perspective, the Boötes Void comprises 0.27% of the observable universe's entire diameter, making it one of the largest known structures in existence. What makes this region truly disturbing is not just its size, but its profound emptiness. Most regions of space contain thousands or even millions of galaxies clustered together through gravitational attraction. The Boötes Void breaks this pattern completely. Within its vast boundaries, astronomers have detected only about 60 galaxies scattered throughout the entire volume. This represents a galaxy density that is roughly 1/10 of what we observe in typical cosmic regions. The mathematical improbability of such emptiness challenges our understanding of how matter distributed itself after the Big Bang. When scientists first mapped this cosmic desert in the 1980s, they struggled to accept what their data revealed. The void appeared so empty that some researchers initially suspected measurement errors or instrumental problems. Follow-up observations using different telescopes and detection methods confirmed the disturbing reality. Here exists a region of space where galaxies are separated by distances so vast that light from neighboring star systems takes hundreds of millions of years to bridge the gaps between them. The few galaxies that do exist within the Boötes Void display unusual characteristics that distinguish them from galaxies in denser cosmic neighborhoods. These isolated star systems tend to be smaller, dimmer, and contain fewer heavy elements than typical galaxies. Their isolation has preserved them in a more primitive state, offering astronomers glimpses into how galaxies might have appeared billions of years ago when the universe was younger and less chemically evolved. Recent computer simulations attempting to recreate cosmic structure formation consistently struggle to produce voids of this magnitude. The models can generate smaller empty regions, but creating something as massive and empty as the Pacific, as the Boötes Void, requires very specific initial conditions that seem unlikely to occur naturally. This computational failure suggests that either our understanding of early cosmic evolution contains significant gaps, or that the void formed through processes we have not yet identified. The gravitational effects of this massive empty region extend far beyond its visible boundaries. Galaxies located near the void's edges show motion patterns that indicate they are being influenced by the absence of matter within the cosmic desert. This gravitational influence operates like a cosmic vacuum, pulling nearby matter toward the void's boundaries while simultaneously preventing new galaxy formation within its interior. The result is a self-perpetuating cycle that maintains the void's emptiness over billions of years. Photons traveling through the Boötes Void experience subtle but measurable changes in their properties. Light waves lose energy as they traverse the empty region, arriving at our telescopes with slightly longer wavelengths than expected. This redshift effect occurs because photons must climb out of the void's gravitational potential well, similar to how light loses energy when escaping from massive objects. The cumulative effect of this energy loss creates observable signatures that astronomers use to study the void's internal structure. The temperature of the cosmic microwave background radiation appears slightly different when measured through the Boötes Void compared to denser regions of space. This temperature variation, known as the integrated Sachs-Wolf effect, provides additional evidence for the void's unusual properties. The effect occurs because the gravitational potential within the void changes as the universe expands, causing photons to gain or lose energy depending on the timing of their passage through the region. Advanced radio telescopes have revealed that even the distribution of dark, Matter appears different within the Boötes Void. Dark matter, which normally provides the gravitational scaffolding for galaxy formation, exists in much lower concentrations throughout the void's volume. This absence of dark matter helps explain why so few galaxies formed in this region, but it also raises questions about how such a large volume of space could remain so devoid of the universe's most abundant form of matter. The void's existence forces astronomers to reconsider fundamental assumptions about cosmic homogeneity. On the largest scales, the universe should appear roughly uniform in all directions, with matter distributed relatively evenly throughout space. The Boötes Void represents a significant deviation from this expectation, suggesting that the universe's large-scale structure contains more irregularities than cosmological models predict. Some theoretical physicists propose that the Boötes Void might represent a fossil remnant from the universe's inflationary period, when space expanded faster than the speed of light during the first fraction of a second after the Big Bang. According to this hypothesis, quantum fluctuations during inflation could have created regions of space with different densities, leading to the formation of massive voids like the one we observe today. The psychological impact of contemplating the Boötes Void cannot be understated. Humans evolved in environments where matter and energy surround us constantly. The concept of such vast emptiness challenges our intuitive understanding of space and existence. An observer placed at the void's center would see no galaxies in any direction, experiencing a level of cosmic isolation that has no parallel in human experience. Recent surveys have identified several other large voids throughout the observable universe, but none approach the Boötes Void's combination of size and emptiness. These discoveries suggest that cosmic deserts might be more common than previously thought, indicating that the universe's structure contains more complexity and irregularity than our models can currently explain. The Boötes Void stands as a monument to the universe's capacity for extremes, demonstrating that cosmic evolution can produce structures that seem to defy the very principles that govern matter and energy. Yet this cosmic emptiness pales in comparison to objects that challenge not just our understanding of space, but of time itself. The impossible star that shouldn't exist. Deep in the constellation Horologium sits a star that has puzzled astronomers for decades. HD 14283, commonly known as the Methuselah star, initially appeared to challenge our understanding of cosmic history, with age estimates that seem to exceed the universe itself. Early calculations suggested this ancient giant was 14.5 billion years old, creating an apparent paradox since the universe measures approximately 13.8 billion years old. This discrepancy sent shockwaves through the astronomical communities and forced scientists to re-examine fundamental assumptions about stellar evolution and cosmic timelines. The Hubble Space Telescope provided the key to resolving this cosmic mystery through refined parallax measurements that determined the star's precise distance from Earth. These improved distance calculations, combined with detailed spectroscopic analysis of the star's chemical composition, led to more accurate age estimates. The refined measurements now place HD 140,283's age at 14.5 billion years with an uncertainty margin of 800 million years. This uncertainty range brings the star's minimum possible age down to approximately 13.7 billion years, which falls comfortably within the accepted age of the universe when accounting for measurement uncertainties. The resolution of this apparent paradox demonstrates how scientific understanding evolves through improved observational techniques and data analysis. What initially appeared to be an impossible object that violated cosmic chronology became a testament to the precision required in astronomical measurements. The star's age now aligns with theoretical models while still representing one of the oldest known objects in our galaxy, formed during the universe's earliest epochs when conditions differ dramatically from today. HD 140,283's composition reveals secrets about the universe's primordial state. Spectroscopic analysis shows it contains virtually no heavy elements, suggesting it formed from gas that existed before the first generation of massive stars died and scattered metals throughout space. Most stars contain traces of carbon, oxygen, iron, and other elements created by previous stellar generations, but HD 14283 remains almost perfectly pure. Its atmosphere consists of roughly 99.9999% hydrogen and helium, with heavy element concentrations millions of times lower than our Sun. This pristine composition places the star among the ultra-metal poor population that formed during the universe's first billion years. These ancient objects serve as time capsules, preserving chemical signatures from an era when only hydrogen and helium existed in significant quantities. The star's survival provides direct observational evidence of conditions that existed shortly after the Big Bang, when the cosmos had not yet been enriched by the nuclear furnaces of massive stars. Recent spectroscopic analysis conducted using advanced infrared spectrometers has revealed additional details about the star's unusual properties. Scientists have detected trace amounts of elements that provide clues about the nuclear processes operating in the early universe. These elements appear to have formed through mechanisms that differ slightly from standard stellar fusion, suggesting that the first generation of stars created heavy elements through processes we are still working to understand fully. The implications of HD 140,283's existence extend beyond a single ancient star. Its discovery has led astronomers to identify several dozen other ultra-metal poor stars with compositions suggesting extreme age. These objects indicate that the early universe produced a population of long-lived stars that have survived from the cosmic dawn. Each new detection adds evidence that stellar evolution in the primordial cosmos followed patterns that current models are still working to explain completely. Advanced computer simulations attempting to recreate the conditions necessary to form such ancient stars have provided insights into early stellar formation processes. The models show that stars forming from primordial gas clouds could indeed achieve the longevity and composition observed in HD 4933. These simulations suggest that the early universe contained pockets of pristine material that remained uncontaminated by heavy elements from previous stellar generations. The search for other ultra-metal poor stars has intensified following HD 140,283's detailed study. Astronomers now scan the sky looking for additional objects with pristine compositions and extreme ages. Large-scale surveys have identified candidates that appear to date back to the universe's first few 100 million years, objects that represent survivors from the cosmic dawn. These searches have revealed that our galaxy contains a hidden population of ancient stars that somehow persisted through billions of years of galactic evolution. The techniques developed to study HD 4283 have revolutionized our approach to understanding stellar archaeology. Scientists can now extract detailed information about stellar ages and compositions that allow them to reconstruct the chemical evolution of the early universe. These methods have revealed that the transition from primordial to metal-enriched star formation occurred gradually over hundreds of millions of years rather than through a single dramatic event. Recent observations have identified similar ultra-metal poor stars in nearby galaxies, suggesting that this phenomenon extends beyond our local cosmic neighborhood. The Magellanic Clouds contain several candidates for primordial stars, while surveys of distant galaxies have detected stellar populations with suspiciously pristine compositions. These discoveries indicate that ancient stars represent a universal phenomenon rather than a local anomaly. The study of HD 14283 has opened new research fields focused on population 3 star candidates and primordial stellar formation. Scientists now recognize that the early universe operated under conditions different enough from today that specialized models are required to explain the observations. This stellar time capsule proves that the cosmos contains objects that preserve information from the universe's earliest epochs, providing direct links to conditions that existed billions of years ago. HD 140,283 stands as proof that the universe contains survivors from its earliest chapters, objects that witnessed the cosmic dawn and continue burning today. Yet this ancient star represents just one type of impossible object that challenges our understanding of how celestial bodies form and evolve. Throughout the cosmos, other phenomena defy conventional explanations about the life cycles of cosmic structures. Zombie galaxies that refuse to die. Among these cosmic anomalies, galaxies that have experienced death and somehow return to life present one of the most perplexing challenges to our understanding of stellar evolution. Astronomers call these cosmic phenomena zombie galaxies because they display characteristics of both dead and living stellar systems. These galaxies appear completely dormant for billions of years with no new star formation occurring within their boundaries, then suddenly begin creating new stars again, as if awakening from an eternal sleep. NGC 1277 represents one of the most puzzling examples of this galactic resurrection phenomenon. This galaxy sits approximately 220 million light-years away in the constellation Perseus and should be completely dead according to current models of galaxy evolution. Its stellar population consists almost entirely of old red stars that formed billions of years ago when the galaxy was young and active. No significant star formation has occurred in NGC 1277 for roughly 10 billion years, making it what astronomers classify as a red and dead elliptical galaxy. Yet recent observations have detected signs of structural complexity that suggest a more dynamic past than its current dormant state indicates. The mystery deepens when astronomers examine NGC 1002-77's internal structure using advanced gravitational lensing techniques. Despite appearing as a typical dead elliptical galaxy, detailed analysis reveals that it maintains the rotational characteristics of a spiral galaxy from much earlier cosmic epochs. This discovery suggests that NGC 1277 experienced what researchers term arrested development, where normal galactic evolution suddenly halted while preserving ancient structural features. The galaxy appears frozen in time, maintaining the kinematic signature of its spiral ancestry while displaying the stellar population of a long-dead system. James Webb Space Telescope observations conducted throughout 2024 and 2025 have revealed that zombie galaxies like NGC 1277 are far more common than anyone previously imagined. The telescope's advanced infrared capabilities allow astronomers to peer through cosmic dust and detect structural indicators that remain invisible to optical telescopes. These observations have identified hundreds of galaxies displaying similar preservation patterns across different cosmic epochs and environments. The data suggests that galactic evolution might involve more complex pathways than the simple progression from spiral to elliptical that dominated previous models. Another compelling example emerged from studies of MAX 2129-1, a massive galaxy observed at redshift Z2 when the universe was only about 3 billion years old. This ancient system displays the mass and structure of a modern elliptical galaxy, but maintains the flat, rotating disk characteristic of spiral galaxies. The discovery challenges assumptions about when and how galaxies transition from active star, forming spirals to passive elliptical systems. MAX 2129-1 appears to represent a snapshot of galactic arrested development, captured at the moment when star formation ceased but before the galaxy's structure could relax into a typical elliptical configuration. The mechanisms responsible for creating these zombie galaxies involve complex interactions between dark matter, environmental factors, and internal galactic dynamics. In dense galaxy clusters, environmental processes can strip away the gas necessary for continued star formation while leaving the galaxy's underlying structure intact. This starvation process occurs gradually as the hot intracluster medium removes cold gas reservoirs that fuel stellar nurseries. The galaxy continues rotating and maintaining its structural integrity even as it loses the ability to create new stars. Dark matter stripping represents another pathway to galactic zombification. As galaxies move through dense cluster environments, gravitational interactions can remove portions of their dark matter halos. This process affects the galaxy's ability to retain gas and maintain active star formation while preserving the stellar component that determines the galaxy's visible structure. The result is a system that appears dead from a star formation perspective, but retains the kinematic and structural signatures of its former active state. Detailed analysis of zombie galaxies has revealed that these systems preserve information about galactic evolution processes that operated billions of years ago. Their stellar populations serve as fossil records of ancient star formation episodes, while their structural properties provide insights into the physical mechanisms that govern galaxy assembly in the early universe. These cosmic time capsules offer unique opportunities to study galactic evolution by examining systems that became frozen at specific evolutionary stages. The implications for galaxy evolution are profound because they suggest that the transition from active to passive systems involves more complex physics than simple gas exhaustion models predict. Traditional theories describe galaxy evolution as a straightforward progression where spiral galaxies gradually consume their gas supplies and transform into elliptical systems through relaxation processes. The discovery of zombie galaxies indicates that environmental factors can interrupt this evolution at specific stages, creating systems that preserve characteristics from multiple evolutionary phases. Computer simulations attempting to reproduce zombie galaxy properties have revealed the delicate balance of physical processes required to create these systems. The models show that specific combinations of mass, environment, and timing must align to produce galaxies that see star formation while maintaining their structural integrity. These simulations suggest that zombie galaxies represent a natural but relatively rare outcome of galactic evolution under specific environmental conditions. The study of zombie galaxies has opened new research directions focused on understanding how environmental factors influence galactic evolution over cosmic time. These investigations examine how galaxy clusters, dark matter distributions, and intergalactic medium properties affect the evolutionary pathways available to individual galaxies. The research reveals that galactic evolution operates as a complex interplay between internal processes and external environmental influences. Recent surveys have identified potential zombie galaxy candidates within our local cosmic neighborhood, providing opportunities for detailed study of the preservation mechanisms responsible for their unusual properties. These nearby examples allow astronomers to examine individual stellar populations and structural components in ways that remain impossible for distant systems detected in deep space surveys. The discovery of these undead galaxies demonstrates that cosmic evolution preserves information about ancient processes in unexpected ways. These systems represent a fundamental shift in understanding how stellar systems respond to environmental changes and suggest that the universe operates according to principles that create lasting monuments to its own evolutionary history. Yet even these mysterious galactic zombies pale in comparison to objects that wield forces so extreme they challenge the very foundations of physics itself. Magnetars, the universe's most dangerous objects. Among these cosmic extremes, magnetars represent the most dangerous objects in the known universe. These stellar remnants are neutron stars with magnetic fields 1 trillion times stronger than Earth's magnetic field. To understand this incredible power, consider that Earth's magnetic field protects us from solar radiation and creates the beautiful aurora displays we see at the poles. A magnetar's magnetic field is so intense that it would completely overwhelm our planet's protective barrier from distances that seem impossibly far away. The destructive capability of these stellar remnants extends far beyond anything humans have ever encountered. A magnetar positioned at half the distance between Earth and the Moon would wipe out every credit card on our planet through magnetic interference alone. The magnetic field strength becomes lethal to human life at much greater distances than most people realize, where the intense magnetic forces would disrupt biological processes in ways that remain difficult to comprehend. No other cosmic object poses such a direct and immediate threat to life from such vast distances. Recent discoveries in 2024 and 2025 have revealed magnetars hiding in our galactic neighborhood that astronomers did not know existed until now. Advanced X-ray and gamma-ray telescopes have detected signatures from these objects that were previously masked by intervening dust clouds or overshadowed by brighter stellar companions. The Imaging X-ray Polarimetry Explorer made the first ever polarization measurements of a flaring magnetar designated 1E1841-045, located approximately 28,000 light-years from Earth within the supernova remnant KES 73. These observations revealed that X-ray emissions from magnetars become more polarized at higher energy levels while maintaining consistent directional properties. The violent birth process that creates these cosmic monsters begins with the most massive stars in the galaxy. When stars containing at least 25 times the mass of our Sun reach the end of their nuclear burning phase, they undergo catastrophic gravitational collapse. The star's core compresses to incredible densities where protons and electrons are crushed together to form neutrons. This collapsed core becomes a neutron star with a diameter of only 12 miles, yet containing more mass than our entire Sun. The extreme compression and rapid rotation during this collapse process generates magnetic fields of unimaginable strength. The physics-defying properties of magnetars challenge our understanding of matter and energy under extreme conditions. Surface temperatures reach millions of degrees, hot enough to vaporize any known material instantly. These stellar corpses rotate at speeds that blur the boundary between reality and impossibility, completing full rotations in seconds while maintaining structural integrity despite centrifugal forces that should tear them apart. The magnetic field strength approaches the quantum critical limit, where the vacuum of space itself begins to behave like a solid material. At these field strengths, empty space becomes birefringent, splitting light into multiple components like a cosmic crystal. Star quakes occurring on magnetar surfaces release more energy than the sun produces in 100,000 years. These seismic events happen when the neutron star's crust fractures under the immense stress created by shifting magnetic field lines. The crust consists of crystallized neutrons arranged in structures stronger than diamond, yet the magnetic pressures can shatter this material like glass. When these fractures occur, they release magnetic energy equivalent to the total energy output of billions of stars. The December 27, 2004 flare from SGR 1806-20, located approximately 50,000 light-years from Earth, released an estimated 10 to the power of 46 ergs of energy and produced enough heavy elements to equal 1/3 of Earth's mass in gold and platinum. The March 5, 1979 event from SGR 0525-66 in the Large Magellanic Cloud demonstrated the incredible reach of magnetar outbursts. This flare released approximately 10 to the power of 44 ergs of energy and was detected by multiple spacecraft throughout the solar system. The gamma-ray burst was so intense that it saturated detectors and caused measurable effects in Earth's upper atmosphere despite the magnetar's distance of roughly 160,000 light-years. The event provided the first clear evidence that magnetar flares could influence planetary environments across intergalactic distances. The 2004 flare from SGR 1806-20 caused measurable ionospheric effects on Earth, demonstrating that these cosmic events can influence our planet's atmospheric chemistry from distances of 50,000 light-years. The gamma radiation interacted with atmospheric molecules in ways that temporarily altered the ionosphere's electrical properties. Radio communications experienced brief disruptions, and satellite instruments detected unusual electromagnetic signatures that persisted for several hours after the initial burst. This event proved that magnetar outbursts represent genuine threats to technological systems even when originating from distant regions of the galaxy. Gamma-ray observations conducted throughout 2024 and 2025 have revealed that magnetars remain active for much longer periods than scientists previously predicted. Traditional models suggested that these objects would lose their magnetic field strength relatively quickly on cosmic timescales, becoming dormant within a few million years. However, recent data shows magnetars maintaining high levels of activity for tens of millions of years, indicating that their magnetic field decay occurs much more slowly than theoretical calculations predicted. This extended activity period means that many more magnetars exist in our galaxy than originally estimated. The closest known magnetar to Earth creates ongoing concern among astronomers who monitor its behavior for signs of increased activity. SGR 0501+4501+4516 travels through the Milky Way at speeds exceeding 110,000 miles per hour, following a trajectory that suggests it did not originate from a typical supernova explosion. This magnetar's unusual motion patterns indicate it might have formed through the direct collapse of a white dwarf star, a formation mechanism that could explain the origin of other mysterious phenomena, including fast radio bursts. Research into magnetar formation scenarios has revealed that these objects might be more common than previously thought. Only about 30 confirmed magnetars have been identified in the Milky Way, but this number likely represents a small fraction of the total population. Many magnetars probably remain undetected because they are not currently active, or because their emissions are directed away from Earth. The discovery that some magnetars form through white dwarf collapse rather than supernova explosions suggests that multiple pathways exist for creating these dangerous objects. Future space missions, including NASA's Compton Spectrometer and Imager scheduled for launch in 2027, will provide more detailed observations of magnetar behavior and help scientists understand the mechanisms behind their extreme outbursts. These advanced instruments will detect gamma-ray emissions with unprecedented precision, allowing researchers to study the internal structure of magnetars and predict their future activity levels. The study of magnetars continues to reveal new aspects of their role in galactic evolution and heavy element production. recent analysis suggests that magnetar flares contribute up to 10% of the gold, platinum, and other precious metals found throughout our galaxy. These stellar corpses represent just one category of cosmic objects that challenge our understanding of physics, yet they pale in comparison to black holes that break reality. At the center of Galaxy M87 sits a gravitational monster that has redefined our understanding of cosmic extremes. This supermassive black hole contains approximately 6.5 billion times the mass of our Sun, creating a gravitational field so intense that it warps space-time in ways that challenge human comprehension. The Event Horizon Telescope captured the first direct image of this cosmic giant in 2019, revealing the shadow cast by its event horizon against the glowing matter spiraling toward destruction. The image provided visual confirmation of Einstein's predictions about how massive objects distort the fabric of reality itself. The M87 black hole demonstrates gravitational effects that operate on scales beyond anything found elsewhere in nature. Matter falling toward this cosmic giant accelerates to incredible velocities, heating the temperatures of billions of degrees as it spirals inward through the accretion disk. The intense magnetic fields generated by this process launch jets of plasma at 99% the speed of light, creating beams that extend for thousands of light years beyond the galaxy's boundaries. These jets carry more energy than the combined output of millions of stars, yet they originate from a region smaller than our solar system. Recent observations conducted throughout 2024 and 2025 have revealed that supermassive black holes like M87's central giant formed much earlier in cosmic history than theoretical models predict. These gravitational monsters appear in galaxies that existed when the universe was less than 1 billion years old, yet they already contained billions of solar masses. The rapid growth required to reach such enormous sizes within the available timeframe challenges current understanding of how matter accumulates around black holes in the early universe. The environment surrounding M87's black hole creates conditions that push the boundaries of known physics. Gravitational time dilation becomes so extreme near the event horizon that time passage slows dramatically relative to distant observers. An object falling toward the black hole would experience normal time from its own perspective, but observers watching from a safe distance would see the object's movement slow to a crawl as it approached the point of no return. The falling object would appear frozen in time to outside observers, its image gradually redshifting until it faded from view entirely. The Event Horizon Telescope's polarized light observations of M87's black hole have revealed intricate details about how space-time becomes distorted in the immediate vicinity of the event horizon. The polarization patterns show how magnetic fields become twisted and amplified by the black hole's rotation, creating conditions that accelerate particles to nearly the speed of light. These observations provide direct visual evidence of how massive objects warp space-time according to Einstein's general relativity predictions. The information paradox represents one of the most profound mysteries surrounding black hole physics. When matter falls past the event horizon, it carries information about its quantum state into the black hole's interior. According to general relativity, this information becomes permanently trapped and eventually destroyed when the black hole evaporates through Hawking radiation. However, quantum mechanics states that information cannot be destroyed, creating a fundamental conflict between two of our most successful physical theories. Advanced computer simulations developed throughout 2025 have revealed how matter behaves during the final moments before crossing the event horizon. The simulations show that material forms an incredibly hot accretion disk that spirals inward while being heated to temperatures of millions of degrees. Magnetic field lines become twisted and reconnect violently, launching jets of plasma at speeds approaching the speed of light. These jets can extend for thousands of light years beyond the black hole, creating some of the most energetic phenomena in the universe. The supermassive black hole at M87's center influences the evolution of its host galaxy across cosmic timescales. The energy released by matter falling into the black hole regulates star formation throughout the galaxy by heating and dispersing gas clouds that would otherwise collapse to form new stars. This feedback mechanism explains why the most massive galaxies contain the largest supermassive black holes, creating a relationship between galactic evolution and black hole growth that operates over billions of years. Theoretical physicists have proposed that black holes might serve as cosmic generators that create new universes through processes we cannot directly observe. The Big Bang might represent a white hole eruption connected to a black hole in a parent universe, making our entire cosmos the interior of a higher dimensional black hole. This model explains why the observable universe appears to be expanding uniformly in all directions while maintaining the same physical laws throughout its volume. The study of primordial black holes has revealed that these objects might have formed through direct collapse of matter in the early universe rather than through stellar evolution. Density fluctuations in the first few minutes after the Big Bang could have created regions massive enough to collapse directly into black holes without first forming stars. These primordial black holes might explain the rapid growth of supermassive black holes in early galaxies while also accounting for some of the mysterious dark matter that dominates cosmic structure formation. Recent theoretical work suggests that the interior of black holes might contain entire universes with their own physical laws and evolutionary histories. The singularity at the black hole's center represents a region where our current understanding of physics breaks down completely, potentially hiding realities that operate according to principles we have never encountered. These gravitational monsters represent portals to physics we do not yet understand, where space, time, and matter behave in ways that challenge every assumption about how the universe operates. Yet these cosmic giants, for all their gravitational dominance, represent only one category of mysterious objects that populate our galaxy. Throughout the darkness between stars drift countless worlds that have escaped the gravitational bonds of their parent systems, creating a hidden population that vastly outnumbers the planets we can observe. Rogue planets in the cosmic dark. These wandering worlds represent just one type of cosmic nomad that travels through the galaxy's vast emptiness. The space between stars contains far more than the darkness suggests, populated by objects that challenge our understanding of how celestial bodies move through the cosmos. Recent gravitational microlensing surveys conducted throughout 2024 and 2025 have revealed that free-floating planetary mass objects drift through interstellar space in numbers that exceed previous estimates. These isolated worlds, detected when their gravity briefly magnifies the light from background stars, appear to outnumber the stars themselves by significant margins. The Nancy Grace Roman Space Telescope project has identified thermal signatures from several of these objects within our galactic neighborhood, using sophisticated infrared detection methods that can spot faint heat emissions from worlds that have been cooling for millions of years. The formation mechanisms responsible for creating these isolated planetary mass objects remain subjects of active investigation. Gravitational interactions within young stellar systems can eject planets during the chaotic early phases of system evolution, when orbital configurations remain unstable. Close encounters between planets or disruptions involving multiple worlds and their host star can accelerate objects to velocities exceeding the escape threshold needed to break free from stellar gravitational influence. Computer simulations show that these ejection events occur most frequently in systems containing multiple massive planets whose orbits become dynamically unstable over time. The detection of these objects relies primarily on gravitational microlensing techniques that observe how their mass bends light from distant background stars. When an isolated planetary mass object passes directly between Earth and a more distant star, its gravitational field acts as a natural lens that temporarily brightens the background star's apparent magnitude. These microlensing events typically last only hours or days, but they provide definitive evidence that massive objects float freely through the space between stellar systems. Advanced infrared surveys have begun detecting the thermal emissions from some of these isolated worlds, revealing objects with masses ranging from Earth-sized rocky bodies to gas giants, several times more massive than Jupiter. The distribution patterns observed in microlensing surveys suggest that these objects concentrate in regions with higher stellar densities, indicating that gravitational interactions in crowded stellar environments produce more frequent planetary ejections than occur in isolated systems. The Nancy Grace Roman Space Telescope, scheduled for launch no earlier than September 2025, will conduct comprehensive surveys designed to map the distribution of free-floating planetary mass objects throughout our galactic region. The telescope's wide-field imaging capabilities and infrared sensitivity will enable detection of these faint objects with unprecedented precision, allowing astronomers to study their properties and estimate their total population within the Milky Way. Theoretical models predict that some of these isolated objects might retain atmospheric envelopes or even maintain subsurface liquid reservoirs through internal heat sources. Radioactive decay within planetary cores can generate thermal energy for billions of years, potentially creating conditions that differ significantly from the frozen surfaces that characterize most objects in interstellar space. The possibility that geothermal processes could operate on isolated worlds expands the range of environments where complex chemistry might occur beyond traditional stellar habitable zones. The study of free-floating planetary mass objects provides insights into the broader processes that shape planetary system architecture and evolution. By examining the properties and distribution of ejected worlds, astronomers can better understand the dynamical interactions that occur during planetary system formation and the factors that determine which configurations remain stable over cosmic timescales. These observations reveal that planetary ejection represents a common outcome of system evolution rather than a rare catastrophic event. Recent microlensing observations have identified several thousand candidate free-floating objects throughout our galactic vicinity, with detection rates that suggest these isolated worlds represent a significant component of the galaxy's total mass inventory. The frequency of microlensing events indicates that encounters with free-floating planetary mass objects occur much more often than previously estimated, raising questions about their potential influence on the long-term stability of established planetary systems. The search for the nearest free-floating planetary mass objects has intensified as detection methods become more sophisticated and sensitive. Current observations suggest that isolated worlds might exist within relatively close proximity to our solar system, potentially close enough to influence the orbital dynamics of objects in the outer regions of our planetary system through subtle gravitational perturbations accumulated over geological timescales. Future observations will focus on characterizing the physical properties of these isolated objects, including their atmospheric compositions, thermal evolution, and internal structure. The data collected by next-generation space telescopes will provide crucial information about planetary formation processes and the prevalence of different types of worlds throughout the galaxy. These studies will help determine whether free-floating objects represent failed planetary cores, ejected super-Earths, or an entirely different category of cosmic body. The implications of discovering such a large population of isolated planetary mass objects extend beyond planetary science to questions about the overall architecture and mass distribution within our galaxy. These wandering worlds fill the supposedly empty regions between stellar systems, creating a hidden population that has remained largely invisible until recent technological advances made their detection possible. The galaxy contains countless objects moving through space at velocities that challenge our understanding of stellar dynamics, carrying with them the signatures of the violent processes that set them on their extraordinary journeys. Hypervelocity stars escaping the galaxy. Among the most extreme stellar phenomena discovered through recent parallax, distance measurements are objects that challenge our understanding of how stars can achieve such extraordinary velocities. Advanced astrometric surveys conducted throughout 2024 and 2025 have revealed stellar objects moving at speeds that seem to defy the gravitational constraints that typically govern stellar motion within our galaxy. The European Space Agency's Gaia mission has revolutionized our ability to measure precise stellar distances and velocities using parallax techniques that determine how stars appear to shift position as Earth orbits the Sun. These measurements have revealed that certain stellar objects display motion patterns indicating they originated from regions with extreme gravitational conditions. The precision of modern parallax measurements allows astronomers to trace the trajectories of these high-velocity objects backward through time to determine their points of origin. Recent analysis of Gaia's parallax data has identified stellar objects with velocities exceeding what traditional galactic dynamics models predict for normal stellar populations. These measurements indicate that some stars have experienced gravitational encounters so extreme that they acquired sufficient kinetic energy to escape the gravitational influence of their original stellar neighborhoods. The parallax-derived distances show that these objects are moving away from the galactic center at speeds that will eventually carry them beyond the galaxy's gravitational boundaries. The physics behind such extreme stellar accelerations involves gravitational interactions operating at the left and 10th scales found in galactic environments. When stellar objects approach regions of extreme gravitational potential, such as the vicinity of supermassive black holes or dense stellar clusters, they can experience what astronomers term gravitational slingshot effects. These interactions convert gravitational potential energy into kinetic energy of motion, accelerating objects to velocities that far exceed their original orbital speeds. Computer simulations developed to explain the parallax measured velocities of these extreme stellar objects reveal that three-body gravitational interactions represent the most efficient mechanism for achieving such high speeds. When binary star systems approach massive gravitational sources, the complex dynamics of the three-body problem can result in one stellar component being ejected at tremendous velocity while the other becomes gravitationally bound to the massive object. This process efficiently transfers orbital energy from the binary system to the kinetic energy of the ejected star. The study of these high-velocity stellar objects provides unique insights into the gravitational environment near our galaxy's central regions. By analyzing the chemical composition and physical properties of stars that have experienced extreme gravitational encounters, astronomers can learn about conditions in the galaxy's most violent regions that would be impossible to observe directly. These stellar messengers carry information about the galactic center's environment preserved from the moment of their gravitational ejection. Parallax measurements have revealed that some of these extreme velocity objects retain evidence of their original stellar formation environments despite experiencing violent gravitational encounters. Spectroscopic analysis shows that certain high-velocity stars display chemical signatures characteristic of stellar populations found in dense cluster environments, suggesting they formed in regions with stellar densities much higher than typical galactic neighborhoods. This chemical evidence supports models indicating that gravitational encounters in dense stellar environments represent a primary mechanism for accelerating stars to extreme velocities. The discovery of stellar objects with such extreme velocities has forced astronomers to reconsider existing models of how stellar populations evolve within galactic gravitational fields. Traditional models assume that most stars remain gravitationally bound to their formation regions throughout their lifetimes, but parallax observations reveal that gravitational encounters can dramatically alter stellar trajectories. These findings indicate that stellar migration through gravitational interactions represents a more significant process in galactic evolution than previously recognized. Advanced telescopic surveys planned for the coming years will extend parallax measurements to fainter and more distant stellar objects, potentially revealing additional populations of extreme velocity stars that current instruments cannot detect. The Nancy Grace Roman Space Telescope and other next-generation facilities will provide parallax measurements with unprecedented precision, allowing astronomers to identify even more subtle examples of stars that have experienced extreme gravitational encounters. The implications of discovering stellar objects with such extreme velocities extend beyond stellar dynamics to questions about the overall structure and evolution of galactic gravitational fields. These observations provide direct evidence that galactic centers contain gravitational environments capable of accelerating stellar mass objects to speeds that approach the escape velocity needed to leave the galaxy entirely. This process represents a mechanism for redistributing stellar material from dense galactic regions to the sparse environments found in intergalactic space. Recent theoretical work suggests that the production of extreme velocity stellar objects might occur in bursts related to specific gravitational events near galactic centers rather than representing a continuous process. Computer models indicate that the disruption of dense stellar clusters or the merger of massive objects could create temporary conditions that accelerate multiple stellar objects simultaneously. These episodic events might explain the observed distribution of extreme velocity stars throughout our galactic neighborhood. The study of these stellar objects has revealed unexpected details about how gravitational interactions operate in the most extreme environments found within galaxies. The parallax-measured trajectories provide observational constraints on theoretical models of three-body gravitational dynamics and help astronomers understand how energy transfer occurs during close gravitational encounters. These observations represent some of the most direct evidence available for studying gravitational physics under conditions that cannot be replicated in laboratory settings. The existence of stellar objects moving at such extreme velocities demonstrates that our galaxy contains gravitational environments, far more dynamic and violent than the relatively peaceful stellar neighborhoods where most stars spend their lifetimes. These discoveries reveal that the cosmos operates according to physical processes that can accelerate matter to speeds that challenge our understanding of how gravitational interactions shape the distribution of material throughout the universe. Yet these visible stellar messengers represent only a small fraction of the matter that actually determines how cosmic structures form and evolve across the vast scales of space and time. Dark matter structures invisible to light. Throughout our galaxy exist massive structures that dwarf every visible object yet remain completely invisible to human eyes. These dark matter scaffolds contain more mass than all the stars and planets combined, yet they emit no light and absorb no radiation. Scientists can only detect their presence through the gravitational effects they produce on nearby matter. The invisible architecture of dark matter creates the cosmic web that determines where galaxies form and how they evolve over billions of years. The mystery surrounding these unseen giants has puzzled astronomers since they first discovered that galaxy rotation curves do not match the predictions of Newtonian physics. Galaxies spin faster than they should based on the visible matter alone, indicating the presence of additional mass that cannot be observed directly. This missing mass appears to be distributed in halos that extend far beyond the visible edges of galaxies, creating gravitational wells that trap ordinary matter and provide the foundation for stellar formation. Gravitational lensing studies conducted throughout 2025 have mapped dark matter distributions with unprecedented precision using advanced techniques that detect how invisible mass bends light from background galaxies. The James Webb Space Telescope contributed crucial observations by identifying subtle distortions in the shapes of distant galaxies caused by intervening dark matter structures. These measurements revealed that dark matter forms complex filamentary networks connecting galaxy clusters across hundreds of millions of light years. The detailed maps show dark matter concentrated in dense nodes where multiple cosmic filaments intersect, creating the framework for the largest structures in the universe. The eerie reality confronting astronomers is that approximately 85% of all matter in the cosmos consists of substances that interact only through gravity. This invisible component outweighs ordinary matter by a ratio of more than 5-to-1, meaning that everything humans can see represents a tiny fraction of the universe's total mass. The implications of this discovery fundamentally challenge our understanding of cosmic composition and suggest that the visible universe represents merely the tip of an enormous iceberg floating in an ocean of darkness. Dark matter particles appear to clump together and collide in ways that scientists are only beginning to understand through advanced computer simulations and observational campaigns. These invisible structures undergo mergers and interactions similar to visible galaxies, but on much larger scales and following different physical rules. When dark matter halos collide, they create gravitational disturbances that can trigger star formation in nearby galaxies or strip gas away from galactic disks. The collision process itself remains largely mysterious because dark matter particles do not radiate energy like ordinary matter, making these cosmic crashes invisible to traditional telescopes. The relationship between dark matter and cosmic voids reveals another layer of complexity in the universe's invisible architecture. These vast empty regions occupy most of the cosmic volume and maintain ultra-low densities that isolate them as cosmic time capsules preserving conditions from earlier epochs. Within these voids, The absence of dark matter creates environments where neutrinos can free stream across enormous distances without encountering significant gravitational interference. This sensitivity to neutrino behavior makes cosmic voids unique laboratories for studying particles that barely interact with ordinary matter. Theories developed in 2025 suggest that dark matter might be composed of primordial black holes that formed during the first moments after the Big Bang. These ancient black holes would have masses ranging from asteroids to stars, creating a population of invisible gravitational sources distributed throughout space. Unlike conventional black holes formed from stellar collapse, primordial black holes could have formed directly from density fluctuations in the early universe without requiring the death of massive stars. This hypothesis explains both the abundance of dark matter and its gravitational effects, while avoiding the need for exotic new particles that have not been detected in laboratory experiments. Advanced simulations running on the world's most powerful supercomputers have revealed dark matter's crucial role in both galaxy formation and destruction processes. These computational models show how dark matter halos grow through accretion and mergers, eventually becoming massive enough to trap ordinary matter and initiate star formation. The simulations also demonstrate how dark matter interactions can disrupt existing galaxies through tidal forces and gravitational heating. Galaxy clusters embedded in dark matter halos can strip gas from smaller galaxies that pass through their gravitational fields, effectively killing star formation and transforming spiral galaxies into elliptical remnants. The search for direct evidence of dark matter particles has intensified with experiments designed to detect these elusive substances as they pass through Earth. Underground laboratories shield sensitive detectors from cosmic radiation while monitoring for the faint signals produced when dark matter particles collide with atomic nuclei. The Lux Zeppelin experiment, located nearly a mile underground in South Dakota, represents the most sensitive dark matter detector ever constructed, capable of identifying interactions involving particles that interact billions of times more weakly than neutrinos. Similar experiments operate in mines and underground facilities around the world, creating a global network of dark matter hunters. Scientists have also developed indirect detection methods that search for the products of dark matter particle annihilation in regions where these invisible substances concentrate most densely. When dark matter particles collide and destroy each other, they might produce gamma rays, neutrinos, or other detectable radiation signatures. The Fermi Gamma Ray Space Telescope and other instruments scan the galactic center and nearby dwarf galaxies looking for excess radiation that could indicate dark matter annihilation events. These observations have placed increasingly strict limits on the properties of dark matter particles without yet achieving definitive detection. Future space missions will provide even more detailed maps of dark matter distributions using improved gravitational lensing techniques and larger survey volumes. The Nancy Grace Roman Space Telescope will conduct the most comprehensive dark matter survey ever attempted, measuring the shapes of billions of galaxies to map invisible structures throughout the observable universe. Ground-based telescopes, including the Vera C. Rubin Observatory, will complement these space-based observations by tracking how dark matter structures evolve over cosmic time. The study of dark matter has revealed that our familiar world exists within a vast invisible universe that operates according to rules we do not yet comprehend. This hidden cosmos contains structures and processes that dwarf anything found in the visible universe, while remaining perpetually beyond direct human observation. Yet even these massive, invisible scaffolds pale in comparison to theoretical defects that might cosmic strings that could slice space. Among the most intriguing theoretical concepts in cosmology are defects that might exist within space-time itself, though their existence remains purely hypothetical. These theoretical structures, known as cosmic strings, represent one-dimensional stars that could have formed during the universe's earliest moments following the Big Bang. Unlike the massive dark matter structures we observe through gravitational effects, cosmic strings would exist as pure geometric defects in the fabric of reality, stretching across vast distances while remaining thinner than subatomic particles. The theoretical framework for cosmic strings emerges from models of the early universe when fundamental forces underwent phase transitions similar to how water freezes into ice. During these cosmic phase transitions, defects could have formed in spacetime geometry, creating one-dimensional objects with properties that challenge our understanding of physics. These hypothetical structures would possess infinite length while maintaining a width smaller than a proton, creating objects with linear mass density so extreme that theoretical calculations suggest a single meter would contain enormous amounts of mass. Gravitational wave detectors operating throughout 2025 have searched for potential signatures that could represent evidence of these theoretical objects. The Laser Interferometer Gravitational Wave Observatory and Virgo detectors analyze their data for unusual patterns that do not match expected signals from black hole mergers or neutron star collisions. Scientists examine these datasets for distinctive frequency patterns that theoretical models predict the cosmic strings would generate as they oscillate and interact with curved spacetime. The analysis focuses on brief bursts of gravitational radiation with characteristics that could only be produced by one-dimensional objects moving at high velocities. The mind-bending properties that cosmic strings would theoretically possess push the boundaries of physical possibility. These objects would combine infinite extension through space with infinitesimal thickness, creating structures that exist in only one dimension while potentially spanning the entire observable universe. The mathematical models describing cosmic strings suggest they would interact with space-time geometry in ways that could create unusual gravitational effects, including the potential to generate closed time-like curves under specific conditions involving multiple strings moving at relativistic speeds. Advanced computer simulations developed to model cosmic string networks predict how these theoretical objects would evolve from the Big Bang to the present day. The simulations incorporate complex physics of string interactions, including scenarios where strings intersect and form loops that would eventually decay through gravitational wave emission. These models predict that cosmic string networks should produce specific spectral characteristics in gravitational wave backgrounds that future detectors might be able to measure with greater precision. The search for observational evidence extends beyond gravitational wave detection to include optical and radio telescope surveys. Scientists scan the sky looking for distinctive lensing signatures that would be produced if a cosmic string passed between Earth and background stars. The gravitational field of a moving cosmic string would theoretically create double images of distant objects, with the images appearing and disappearing as the string moves across our line of sight. Radio telescopes monitor for characteristic pulse patterns that might be generated if cosmic strings interact with dense plasma surrounding pulsars. Analysis of cosmic microwave background radiation has revealed potential temperature fluctuations that some researchers suggest could be consistent with strings moving through the early universe. These temperature patterns appear as straight lines extending across regions of the sky, matching predictions for cosmic strings that existed when the universe was only 380,000 years old. However, the statistical significance of these features remains a subject of ongoing debate within the cosmological community. Laboratory experiments have attempted to create analogous defects in condensed matter systems and superconducting materials to better understand how cosmic strings might behave. These experiments provide insights into topological defect formation during phase transitions while demonstrating that such defects can indeed form in physical systems. The results support theoretical predictions about cosmic string formation during symmetry-breaking events that occurred in the primordial universe, though they operate on vastly different scales than their hypothetical cosmic counterparts. The potential discovery of cosmic strings would provide direct evidence for physics operating at energy scales comparable to those present during the Big Bang itself. These objects would represent fossils from the universe's first moments when fundamental forces operated under unified conditions impossible to recreate in laboratory settings. The study of cosmic strings could reveal how space-time itself formed and evolved during the earliest epochs of cosmic history. Recent theoretical developments have explored how cosmic strings might serve as connections between different regions of space-time, though these concepts remain highly speculative. The mathematics of general relativity suggests that under specific conditions, cosmic strings could maintain stable configurations across cosmological distances, potentially creating geometric shortcuts through space-time. These theoretical possibilities continue to drive research into the fundamental nature of space and time. The search for cosmic strings represents one of many efforts to understand the universe's most extreme theoretical phenomena. Whether these one-dimensional defects actually exist remains an open question that future gravitational wave detectors and observational surveys may eventually answer. The ongoing analysis of gravitational wave data continues to refine our understanding of what signatures these hypothetical objects might produce. While cosmic strings remain theoretical constructs, their potential existence highlights how much we still do not understand about the universe's fundamental structure. These hypothetical defects represent just one category of mysterious phenomena that could influence cosmic evolution on the largest scales. Throughout the cosmos, forces operate that we can detect only through their effects on visible matter, pulling entire galaxies through space toward destinations that remain hidden from direct observation. The Great Attractor's hidden secret. Beyond these theoretical constructs lies a gravitational phenomenon that affects our galaxy's motion through space in ways we are only beginning to understand. Something enormous pulls our galaxy through space at 600 kilometers per second toward a destination we cannot see. This invisible gravitational force lurks behind the disk of our own Milky Way galaxy, where dust and gas block our view of whatever cosmic giant drags us across the universe. Scientists call this hidden force the Great Attractor, and it represents one of the most mysterious gravitational anomalies in our local cosmic neighborhood. The zone of avoidance stretches across roughly 20% of our night sky, where the dense plane of our galaxy blocks observations of distant objects. Behind this cosmic curtain lies a region that has remained largely hidden from human observation for centuries. Astronomers have long suspected that massive structures exist in this obscured zone based on the peculiar motions of nearby galaxies, but direct observation remained impossible using traditional optical telescopes. The dust and gas concentrated in our galactic plane absorbs visible light from background objects, making them effectively invisible to ground-based observations. Advanced X-ray and infrared observations conducted throughout 2025 have finally pierced this galactic veil using wavelengths that can penetrate the obscuring material. The James Webb Space Telescope contributed crucial infrared data that revealed previously hidden galaxy clusters embedded within the zone of avoidance. These observations detected thermal emissions from galaxies that had remained completely invisible to optical surveys for decades. X-ray telescopes simultaneously mapped hot gas distributions associated with massive galaxy clusters that contribute to the Great Attractor's overall gravitational field. The discoveries emerging from these penetrating observations have revealed a cosmic landscape far more complex than anyone anticipated. Massive galaxy clusters containing thousands of individual galaxies sit hidden behind our galactic disk, creating gravitational fields that extend across hundreds of millions of light years. These cluster complexes contain more mass than hundreds of trillions of suns, yet remained undetected until advanced infrared instruments could peer through the cosmic fog. Each newly discovered cluster adds to the total mass responsible for pulling our galaxy toward this mysterious region. Our entire local group of galaxies, including the Milky Way and Andromeda, experience this irresistible gravitational attraction that has been shaping our cosmic neighborhood for billions of years. The local group travels as a unit through space, while individual galaxies within it maintain their relative positions through mutual gravitational interactions. This coordinated motion indicates that the Great Attractor's influence extends much farther than the visible boundaries of the hidden structures themselves. Gravitational effects propagate across cosmic distances, creating a sphere of influence that encompasses our entire region of the universe. Recent surveys have uncovered An even larger structure called the Shapley supercluster that lies beyond the Great Attractor and may represent the ultimate destination of our cosmic journey. The Shapley Attractor contains even more mass than the Great Attractor itself and exerts gravitational influence across distances exceeding 500 million light-years. This discovery suggests that our galaxy participates in a hierarchical system of gravitational attraction where local structures are themselves being drawn toward even more massive, distant concentrations of matter. The mind-bending scale of our galaxy's motion becomes apparent when considering that 600 kilometers per second represents more than 1.3 million miles per hour of sustained travel through space. At this velocity, our galaxy covers distances equivalent to traveling from Earth to the Moon every few hours, while maintaining this incredible speed for millions of years. The energy required to accelerate and maintain such motion across cosmic timescales indicates gravitational forces operating on scales that challenge human comprehension. Detailed mapping conducted throughout 2025 has revealed the true extent of this gravitational influence by tracking the peculiar velocities of thousands of galaxies throughout our local cosmic volume. These surveys show that the gravitational effects extend far beyond the visible boundaries of the attracting structures themselves. Galaxies located hundreds of millions of light-years away from the Great Attractor still show detectable motion in its direction. The sphere of gravitational influence encompasses a region larger than many observable galaxy clusters yet originates from structures hidden behind our own galactic disk. Computer simulations incorporating the newly discovered mass distributions have recreated the observed galaxy motions with unprecedented accuracy. These models show how the complex gravitational landscape channels cosmic flows along preferred directions, creating rivers of galaxies flowing toward regions of highest density. The simulations reveal that our local group follows one of many such cosmic streams, all converging toward the gravitational center hidden behind the zone of avoidance. The mystery deepens when considering what lies at the very center of this cosmic traffic jam. Despite penetrating observations using multiple wavelengths, astronomers still cannot identify the specific objects or structures responsible for creating such enormous gravitational attraction. The region appears to contain multiple overlapping influences from different galaxy clusters and superclusters rather than a single dominant source. This distributed mass creates a gravitational field so complex that predicting its long-term effects on galactic motion requires sophisticated computer modeling. Scientists continue investigating whether the Great Attractor represents a temporary configuration of matter or a permanent feature of cosmic architecture. Galaxy clusters can merge and reorganize over cosmic timescales, potentially altering the gravitational landscape that currently dominates our local motion. Future observations will determine whether our cosmic destination remains fixed or changes as the underlying structures evolve through gravitational interactions and cosmic expansion. The implications extend beyond our immediate cosmic neighborhood, because similar hidden attractors might exist throughout the universe, creating large-scale flows that shape cosmic evolution on the grandest scales. These gravitational giants could represent fundamental organizing principles that determine how matter arranges itself across cosmic distances. Our journey toward the Great Attractor demonstrates that even our galaxy's cosmic address remains subject to forces beyond our immediate observation, revealing that the cosmos operates according to principles that continue to surprise and challenge our understanding of reality itself. These discoveries from 2024 and 2025 have fundamentally expanded our knowledge of cosmic phenomena through direct observation and measurement. The Boötes Void's staggering 330 million light-year diameter demonstrates that emptiness operates on scales we barely comprehend, containing only 60 galaxies across its entire volume. Zombie galaxies like NGC 1277 preserve ancient spiral structures while remaining completely dead for 10 billion years, challenging our models of galactic evolution. Magnetar flares such as the 2004 event from SGR 1806-20 release more energy than our sun produces in 100,000 years while creating heavy elements equivalent to one-third of Earth's mass in gold and platinum. The James Webb Space Telescope continues revealing massive galaxies that formed impossibly early in cosmic history, forcing astronomers to reconsider fundamental assumptions about how the universe evolved from its primordial state to the complex